Welcome to myprojectbazaar.com.
Now we will discuss about the product for toward multi-gigabit wireless design of high throughput MIMO detector with hardware efficient architecture. Next we will see the abstract for the product. In recent year, multiple input multiple output technique have become a promising feature in wireless communications, so that the higher spectral efficiency or better quality of services can be provided. The multiple transmission time is to be increased, so the system performance is to be low for the existing conventional MIMO FDM architecture. The system is mainly focused by the power consumption level and the hardware complexity for the proposed OFDM architectures, and the analyzes the memory blocking in MIMO architecture using the communication system. This paper presents a hardware efficient architecture for 4x4 and 8x8 high throughput MIMO detector. The adopted man constant K-based algorithm tends to keep more several nodes in top search tree layer and reduce the computational complexity in bottom layers as opposed to the conventional K-based algorithm. A pipeline architecture is used to generate one detection output per clock cycle. This meeting multi-gigabit throughput requirement for advanced wireless communication system. The proposed efficient flooding scheme strikes a suitable balance between the complexity and throughput. This paper also presents a discussion on the scalability of the architecture with respect to the setting of QAM sizes and KA values and the antenna numbers. One 4x4 MIMO detector IC has been manufactured and one 8x8 MIMO detector layout has been realized both in 90 nanometer CMOS technology. The 4x4 MIMO detector IC has 232 kilobytes memory occupancy. The maximum measured throughput 4.08 gigabits at 170 MHz operating frequency for the proposed MIMO FDM architectures. The MIMO FDM architectures mainly used for the higher spectral efficiency and better quality service can be provided. Hence, the evaluation of the spatial domain has prompted many researchers to devote themselves to algorithmic and architectural design for high order MIMO detector architecture. Next, we see the flow diagram for the project. First of all, we design the hierarchy based tree architecture design in overall architecture. The VLSI MIMO FDM process is developed by the VHDL coding. The VHDL coding is developed by the structural modeling for our MIMO FDM process. First, we design the MIMO FDM architecture. MIMO FDM architecture consists the IBM and BCM blocks. IBM blocks means input pre-processing module. BCM blocks is parameter calculation module. The two block module is mainly focused by the digital architecture design. The IBM block consists the two sub-blocks, STBC and non-STBC work. STBC is mean space-time block coding, non-STBC non-space-time block coding block. These blocks controlled by the controller block. First, we design the IBM block in our architecture, MIMO FDM architecture. The IBM block consists of two channel allocations for the STBC and non-STBC. The IBM is one of the channel allocation block. Channel allocation block is mainly used to the input signal is passing to the STBC non-STBC. We select the channel, then passed to the STBC output or non-STBC output results. This work is controlled by the controller architecture block. Thus the block is using to the IBM works. Then IBM result is passed to the parameter calculation module. This parameter calculation module is mainly used to the calculate the overall signal parameter results in our IBM block final results. The IBM blocks just detect the channel output result. Thus the result to apply the BCM block. BCM block is considered the squarer and multiplier, then XOR gate blocks and register elements. These logical elements are applied to the BCM block. So first we design the multiplier and squarer unit for the BCM block, then we design the XOR gate operations, and to apply the register element, then we design the BCM block, and finally we connect the IBM and BCM block using to the overall MIMO architecture. Then first of all we design the IBM, and second we design the BGM, then apply the input date channel result and the channel allocation and the channel input, then clock pulses for the MIMO FDM architecture, then pass the IBM block, and finally we detect the channel output for the IBM block, and to apply the BGM block, then BGM block we calculate the parameter output module for the final result. These results are to get the output final result and to simulate and synthesis for the Xilinx OFDM Xilinx 14.2 software. The simulation is only calculate the manual results for applied the input and output result. The synthesis report is calculate the satisfy the three parameters: area, power, delay, speed operations. These parameters to satisfy for the synthesis report. Finally, we see the output for the product. First of all, we open the MIMO design Xilinx ISC project. Then select the simulation, and to select the simulate behavioral model, just we open the ISM simulator for the simulation process. Then create the simulation result, just we apply the binary input result and to get the output final result for the MIMO OFDM process. Then apply the input for the clock signal and set the reset function to deactivate the enable function. Then apply the channel selection and channel count for the IBM and BGM process. Then to apply the binary process input results for the channel data, any of the 8-bit data to apply the channel input processor. Then apply the input selection signal for two 8-bit data signals. Then to run the time specified on the toolbar, then apply the clock 1 logic, then run and apply the another clock signal to in MIMO FDM process. Then deactivate the reset function and activate the enabling function. Then set clock 1 logic. Just we calculate the zoom to full view functions. Then create the D1 to D3 function for the OFDM process, and we calculate the parameter calculation module result for the output process. Then close the simulation result and we calculate the synthesis report result. Just we select the implementation and you run the view RTL schematic diagram. Then add and create schematic. Just double click the block. This RTL diagram represent the what are the logical blocks present in the MIMO FDM process. Then calculate the view technology and calculate the view technological schematic diagram. Add and create schematic. Just double click the process. Then create the IBM block for the view RTL schematic diagram. This schematic diagram which represent the what are the lookup table and input output, bounded input output, and wire length and wire connections, and then flip-flop pairs placement for the technological diagrammatic representation. Then go to the design summary process. Just we select the synthesis report result and down of the report, we calculate the area of the MIMO FDM process, the slices LUT and flip-flop pairs, then bounded input-output to calculate the area of the OFDM architecture process. Then calculate the timing summary results. The minimum period is 7.298 nanoseconds and frequency level is 137.031 MHz. Then latency level to be after and before clock calculations. The delay time is 2.091 nanoseconds process. Just then finally we calculate the power calculations for the process. Just